Now, section 6.4. Let's start number 9. Is it change the exponential statement to an equivalent statement involving a logarithm? Okay, the conversion is the base is 3. So you write logarithm. Logarithm is the word logarithm. Okay, number 9. The base is 3. You put the small number here, 3. Of 9, and the answer is always the exponent. The answer of the logarithm always is exponent, case 2. Now 11. 11 is exactly the same. Is logarithm. The base is 8 of 1.6 is equal to, it's exponent. 13 is logarithm base 2 is the base of 7.2 should be the exponent is x. 15 is logarithm and the base is e of 8 is equal x. In this case, when this logarithm base e, the frequently notation is using natural logarithm. Lm of a is equal x. Okay, this is much better answer. Okay, let's see 17. Now it's opposite. Change the logarithm statement to equivalent involving exponent. It's exponential. The base is 2. The exponent is 3 is the answer of the logarithm, and the answer is 8. This is 17. 19. 19 is the base is a. The exponent is 6 equal 3. Remember, the exponent is the answer of the logarithm. 21. The base is again 3. The exponent is x, and the answer is 2. And 23. 23 is the base is, well, it's ln, so the base is e. E to the x, que es the exponent, que is the answer, is equal 4. Okay, this is the conversion. Okay, 25, 27, 29, 33, 31, 35. Let's find the exact value of each logarithm without using the calculator. Just using only constant. Okay, logarithm of any base of 1 is 0. Okay, the proof is easy. See, you convert to exponential. The base is 2, the exponent is 0 equal 1, right? The exponent is necessary to raise any base in order to get 1 is 0. The logarithm of 1, this is a fundamental property. Now 27. 27 is logarithm base 5 of 25 is equal to x. It's obvious too, because what x exponent can necessarily raise 5 in order to get 25 is 5 to the second power. But let's try to do it in a different way. For example, let me try to apply systematic way. Is suppose the base is 5, the exponent is x, is equal to the rest, que is 25. At 25 I know very well que is 5 to the second power. So if this is equal to that, then the exponents are the same, and the answer is x equal to. Okay, now 29. 29, 20 9 is logarithm of base 1/2 of 16 equal, I don't know. Okay, in this case, no obvious. So you convert to exponential. The base is 1/2, the exponent is x, the answer is 16. Now we have exponential equation, and you manipulate this using the common base. In this case, I know that 1/2 is 2 to the negative 1. Okay, I know also that 16 is 2 to the 4 power. And so this is 2 negative 1 raised to the x power is equal to 2 to the 4 power. Now multiplication is 2 to the negative x is equal to 2 to the 4 power. If then two exponentials are the same and the base is the same, it's because the exponents are the same. Therefore, s minus x equal 4, and you divide by negative 1, both sides, and you get the final answer is x equal negative 4. That was 29. 31 is logarithm of base 10. 31. 31. Logarithm base 10 of the radical 10. No. The base is 10, the exponent is x, and this is radical 10. And radical 10 is obvious, it's 10 raised to the 1/2 using fraction exponent. Now the conclusion is, if this is equal to that, and the same base, the exponents are the same. Is 1/2. 31. 31. 33. Okay. 33 is logarithm square root 2. 33. Logarithm of the base is square root 2 of 4. No? Is 4? Oh yes, it's 4. I don't know. Question mark. Convert to exponential. The base is radical 2. The exponent is x is equal 4. Now I know very well que square root 2 you can express like a 2 raised to the 1/2, and 4 is 2 to the second power. This is 2 raised to the 1/2 raised to the x is equal to the second. So no, you multiply the exponent is 2x over 2 is equal to 2 to the second. Okay, you want to exponential and the base is the same is because the exponents are the same. Now multiplication by 2 both sides, multiplication 2 here and 2 here. The answer then is x equal, cancel out this and this, 4. 2 times 2 is 4. That was number 33. Now 35. 35 is ln square root e. 35. 35 is ln square root e. Okay, the only thing you need to know is ln is equivalent to say logarithm base e. So the base is e. When you convert to exponential, it's e. E is the base. The exponent I don't know is x is equal to radical e. And radical e is e to the 1/2. Now if this exponential is the same, then the conclusion is x equal 1/2. Okay? Let's continue the homework for the section 6.4. Let's find the domain of each function que contain a logarithm expression. Let's do the 37. Okay, the basic idea is when you have logarithm of any base, it doesn't matter the base, and inside we have one expression, the domain is, the restriction for finding the domain is this expression must be positive. neither 0 nor negative. Okay, that's the only problem. So now, so you want to do the 37. 37 is, you take the expression inside the logarithm. It doesn't matter what base is, in this case natural z. Well, this is x minus 3 greater than 0, x greater than 3, and the domain. The domain of the function f is x such that x is greater than 3, no equal 3, just greater than or equal. Now, next one is 39. 39. Okay, 39 is exactly the same idea. Is you take the expression inside, because x squared must be positive. So in this case, we have a polynomial inequality, right? So now is you convert to equation. It's obvious is x equals 0 is the critical value. Maybe analyze the number line. 0 is the middle here. And you select arbitrary testing. Suppose -1 and +1. Let's see what happens. In the testing point, the only factor that we have is a testing point, and the only factor that we have is x squared. -1 and +1. For -1 squared is positive, and for +1, sorry, is again positive. And the statement is greater than 0, because both are true. So what is the domain? The domain is all real number, positive number, and negative number, but in 0 we have a hole, because 0 is not inside the problem, because it's greater than 0, no include equal, because this inequality is a strict inequality. So basically the domain of the function, let me see what name is the function, capital F. Domain of the capital F is from -infinity, 0, no include 0, union 0, infinity. Oh, another word is x such that x must be different to 0. Okay? That was 39. The next is 41. Okay, the same thing. In 41, you take the expression inside the logarithm, x over 2 minus 5 must be positive. That says x over 2 greater than 5. Multiply the whole thing by 2. 2 here and 2 here. Is cancel out this part. Is x greater than multiplication. This is 10. And the domain of the function f is x such that x is greater than 10. Well, it's equivalent to say 10, infinity. 44. Now 43 is here. 43. You take the expression inside the logarithm. I don't care the base. It's 1 over x plus 1. 1 over x plus 1 greater than 0. In this case, you apply the rule number 4 of the inequality. And when you see this expression must be positive, and 1 is positive, is because x plus 1 is positive. So x greater than minus 1. Then the domain of the function, what is the name of the function in this case? Function f is x such that x is greater than negative 1. That was question, what number of question is 43. This is what 43. Now 40 something, 45 here, 45. Okay, 45 is x plus 1 over x. 45 is x plus 1 over x greater than 0. Now you determine, in this case, is typical rational inequality. You determine the critical value as negative 1, and you determine the restriction. There's a restriction and critical value. Let's do it in the partition. The partition is infinity, negative infinity, 0, and negative 1. The testing maybe is negative 2, negative half, and positive 1. And the chart, the changing sign of chart is TP. The factor is x plus 1, x and total. The testing is minus 2, negative 1/2, and 1. Okay. Negative 2 here is negative. Negative 2 here is negative again. Now the answer is positive. Negative 1 here is positive. This is negative, this is negative. And 1 here is positive, and it's positive. Therefore, the part is true, corresponding with the positive part, is this and this. That is this part, and also this part. And of course, do not include the restriction, parenthesis, and yes, include the critical value. No, not include, because it's not equal here. No include, hello. Okay, now, domain conclusion. Domain of the function, what is the name of the function? This function? G. Domain of G is from negative infinity, comma negative 1, union, 0, comma infinity. If you want another notation is x such that x is less than negative 1, or x greater than 0. This is 45. Now let's see 47 is the last one. 47 is the last one. 47 and 49 no? No, 49 no. 47. 47 is the square root natural logarithm. 47 is square root natural logarithm of x. So in this case we have two restrictions. What is the first restriction? The first restriction is that the expression inside the radical must be greater than or equal to 0. So el logaritmo of 0, logarithm of 1 is 0. So you interpret this what are the bunch of values that satisfy this condition? Okay, to be 0, so when x is equal 1, logarithm 1 is 0. Okay, now the value that is positive is the value bigger than 1. So basically this represents like when the x is greater than or equal 1. Because the value less than 1 is negative logarithm. For other part, this is one restriction. Restriction 1 is the expression inside the logarithm Sx must be positive. So now basically the answer is x must be positive and x greater than or equal 1 together, right? The intersection is intersection, remember, is infinity, negative infinity, this is 0, this is greater than 0, and greater than or equal 1 is bracket here and here. Therefore it's obvious that the intersection is this part that includes of course 1, and the domain of the function, what is the name of the function in this case, is f is bracket 1 comma infinity, or in other way expressed in the other notation is x such that x is greater than or equal 1.